All right, so we've got our last topic for the class. I'm sure you guys are so excited to not have to put up with my crap anymore. Today we're going to be talking. Did you say I am actually? You've got like at least 3 more years of dealing with my crap. I just meant from a student perspective, but yeah. With any luck, you'll be my boss in a couple of years. All right. So today we're going to be talking about power factor correction. And this goes into the topic of power factor that we were talking about in our last class, right? So in our last class meeting, I had mentioned that average power is what we as consumers pay for, and apparent power is what the electric utility has to pay to generate. So that realistically, they want the ratio of those two quantities to be as close as as possible. Unfortunately, that will not happen if you have large industrial scale inductive loads. So I'm going to draw a power triangle for a large inductive load, right? So here's my imaginary axis. Here's my real axis. Let me make that line a smidge straighter. And here is my complex power, S, and I'm going to call this S old, representing the complex power prior to our applying a power factor correction technique. Excuse me. So the projection of this complex power onto the real axis will give us P old. The projection of the complex power onto the imaginary axis will give us Q old. And we are forming an angle, theta old, between our complex power. I don't care about my virus protection. I still don't care about my virus protection between the complex power vector and the positive real axis. So if I want my power factor to be larger or closer to 1, does that angle need to get larger or smaller? Smaller, right? So the cosine of 0 is 1. So the closer that we can get that angle theta to 0, the higher our power factor will be. Okay? So there are 2 ways to do this from a mathematical standpoint, one of which is completely and utterly asinine, and the other of which is what is actually done. So let's talk about the completely and utterly asinine version first. Okay. So let's say that I were to increase the amount of average power my load consumes by increasing its resistance. Okay. I might see something like this. So here's S new, and we can see that our angle is indeed smaller, which means our power factor will have been corrected. Why this is completely and utterly asinine is because we are increasing our average power, which means we are paying more in utility costs in order to avoid paying a fine, which makes no sense whatsoever, right? So mathematically this works. In a practical sense, this is about as dumb as you could possibly do things, okay? So instead, let's consider what would happen if we were to reduce the amount of reactive power absorbed in our system, right? So if we held P old to be constant and we made Q smaller, we might have something like this. So this would be S nu. This would be Q nu. And this angle would be theta nu. We've achieved power factor correction because our angle is smaller, so our power factor will have increased. Our average power did not change at all, so we did nothing to run up our utility bill or anything like that. So we should see that we're operating at the same cost over a long term while having a better power factor. So my question to you guys is, how might we accomplish this? Well, in our last class meeting, we looked at the complex power absorbed by resistors, capacitors, and inductors, right? We found that the complex power absorbed by a resistor was always a positive real quantity, which actually would have been the first case scenario, right? So if we add resistance, that's what we would have gotten. With an inductance, we found that inductors always absorb reactive power, which would actually make Q get larger. Capacitors supply reactive power, where supplying reactive power is the negative of absorbing reactive power. So it looks like we just need to add capacitance into the system. So typically speaking, if we had a simple system where we have some voltage source I'm going to give myself a set of terminals here. And then we had, this is an impedance that's representative of a transmission line. And then this is an impedance representative of the load we are trying to power. Power factor correction simply involves placing some capacitance C in parallel with our source. Now, technically speaking, we could correct the power factor at the load as well. So put the capacitor bank in parallel with that ZL. However, our transmission line is also typically going to be an inductive load. It's going to be significantly smaller than our actual load. But putting our capacitance in parallel with the voltage source corrects for both the transmission line characteristics and the load characteristics. So this is typically where it'll be done. All right, so we have an idea of what we're doing. Now let's go through some math. So let me put this in this light blue thing here, right? So this difference between these quantities is the amount of reactive power that our capacitor has to supply, right? So if we define S old to be P old plus JQ old, and we define S new, our complex power after power factor correction, to be P old plus JQ new, then the complex power that our capacitor needs to provide is S new minus S old, which will come out to be P old plus JQ new minus P old plus JQ old. The P olds wind up canceling each other out. and we're just left with J Q new minus Q old, or J Q cap. Now, this Q cap quantity, I'm going to put a note here, will always be a negative quantity because the capacitor is supplying bars into our system. Okay? So usually we don't actually bother or care about the complex power. We're interested in finding out what specific value of a capacitor is going to get the job done, right? So what we can do is we can put this relationship for the complex power absorbed by a capacitor and set it equal to the complex power absorbed by a capacitor that we derived last Friday, right? So that other relationship, which I'll put over here, was negative J omega C times, do it this way, the voltage drop across the capacitor, magnitude of the voltage drop across the capacitor squared. So if we equate those two relationships and solve for C, what we'll find is that our capacitor value C is equal to negative Q cap divided by omega times the magnitude of the voltage drop across the capacitor squared. And we can actually go one step further here, and we can express this in terms effectively of our current power factor and our target power factor. Right? And so that's going to look like positive P old times the tangent of theta old, which is directly related to our old power factor, minus the tangent of theta new, all divided by that same denominator, omega times the magnitude of our capacitor voltage squared. So if you look on your practice exams and all of that kind of good stuff, you'll see effectively that you're usually provided with enough information to figure out most of these things pretty directly, just using simple relationships. Instead of working an easy example problem that is representative of what you're going to see on your exam, I'm going to choose to work a web work problem that is a huge pain in the butt to really get into the nitty-gritty of how this thing works. So this will save you guys hopefully a little bit of headache when you're doing your homework for this material. Bless you. So homework set number 24. I think it's problem 4. Yeah. So this is the problem that we're going to be looking at. We are told that in the circuit below, our resistor has a value of 5.7 ohms. Our load is drawing 14.7 kilovolt amperes at a power factor of 0.5 lagging. That is an atrocious power factor. If the magnitude of our load current is 21 amps RMS, what must the value of our capacitor be to cause the source to operate at a power factor of 0.95 lagging if the source operates at 60 hertz, okay? So I'm going to write this stuff down really quickly, slightly more. So here's our source voltage Vs. Here's our capacitor C. Here's our resistance, which if I'm remembering correctly is 5.7 ohms. Here is our load. Which we are told draws 14.7 kVA at a power factor of 0.5 lagging. Here is our load current, and we're told that the magnitude of this load current is 21 amps RMS. And we want the power factor at which our voltage source operates to increase to 0.95 lagging, and our goal is to determine the value of the capacitor that accomplishes this. Ashton, you look new. Let me make my penmanship slightly less crappy. All right. So before I just tear into this, does anybody have any thoughts about what we might wind up doing to get this? And I've intentionally left the equation up above so that we can kind of have a checklist for the pieces of information that we need. Okay. So anybody have any thoughts on what we might be doing here? Oh, and another piece of information that we were given, sorry, was that F is 60 hertz. So I'm of the opinion that we should take care of the lowest hanging fruit first, right? So we have 5 different quantities to plug into our equation. We need to figure out what P old is. We need to figure out what theta old is. We need to figure out what theta nu is. We need to figure out what omega is. And we need to figure out what the magnitude of VC is, right? We have those 5 pieces of information. Then we have everything that we need to just plug into this equation and be done, okay? So in my opinion, the easiest piece of information for us to figure out right now would be omega. It's actually the only thing that we were explicitly told, or pretty much explicitly told, right? So omega is nothing more than 2 pi f. So that would be 120 pi radians per second, which means we are 20% through. I believe that we have enough information to calculate theta nu as well, because theta nu should just be the inverse cosine of the power factor at which our voltage source operates. So the inverse cosine of 0.95 lagging is 18.195 degrees. And I'm going to store this in my calculator as A. So now we have 2 of the 5 pieces of information that we need. So let's talk about the other pieces. Well, P old and theta old are going to be related to each other. So if we can figure out what the complex power absorbed by our system is, or what the complex power supplied by our source is prior to power factor correction, we will have both of those pieces of information. The magnitude of the voltage drop across the capacitor is just the magnitude of the voltage drop supplied by our source, which was not given to us, but at least we know what we're looking for, right? So DC is just going to be VS, so we just need to solve for VS in whatever way we can. All right, so let's start by finding the complex power absorbed by our load. So I'm going to call this S load. What do I need to do to find this complex power? We worked a problem just like this last Friday, right before we left. Exactly correct. Yeah. So we were provided the apparent power because we were told that the load is drawing 14.7 kilovolt amperes. So the units there explicitly tell us that we're dealing with apparent power. So we would need the apparent power and our angle. And Liam has suggested that our apparent power is just 14.7 kVA, for which he is absolutely correct. And in order for us to find our angle, we simply take the inverse cosine of the power factor at which our load is operating at, which would be 0.5. Because our load is operating at a lagging power factor, this angle should be positive, which is why I'm not changing the sign on the inverse cosine operation. And so I can say 14.7 times 10 to the 3 inverse cosine 0.5 looks like 14,700 angle 60 degrees volt amperes in polar form and 7,350 plus J 12,730.573 kVA in rectangular form. So what two pieces of information did we just get? Well, actually, sorry. We didn't get either of the pieces of information. We just got significant closure or something. I forgot about the resistor absorbing power. So let's take that into account really quickly, right? So we just figured out the complex power absorbed by our load. Now let's figure out the complex power absorbed by our resistor. So using our alternative relationships, we know that this should just be the magnitude of the current flowing through the resistor times the resistor value itself. So that's going to be 21 amps RMS squared times 5.7 ohms. Double check and make sure it is 21. Yeah. And that is 2,513.7 angle 0 degrees volt amperes, or 2,513.7 plus J0 VA in rectangular form. Now, I can say that the complex power supplied by my voltage source is simply the sum of the complex power absorbed by my load and the complex power absorbed by my resistor. Which comes out to be 16,104.660 angle 52.23. Or 9863.7 plus J 1270, 730.573. Yay, that shouldn't have K there. All right, now, sorry for the mistake there. What two pieces of information that are necessary to us calculating for C did we find? What's that? So we found P old. So what's P old going to be? Yep. So this guy right here is P old. What other piece of information did we get? Someone other than Liam. Right, but is reactive power literally anywhere in our equation? So just to point things out, we figured out P old, we figured out theta nu, we figured out omega. So by process of elimination, we either just found theta old or VC. Which of those two do you think it might be? I'll give you a hint. At no point have we calculated a voltage. Theta old. This guy right here is theta old. Complex power angle supplied by our source prior to power factor correction. So the last thing that we have to figure out is our source voltage. So this is probably one of the tougher things to do. And realistically, it's not all that tough. We just kind of have to make an assumption. So we know actually, we don't even have to make an assumption. So SVS old is going to be our source voltage VS multiplied by the complex conjugate of our load current. We don't have the complex conjugate of our load current because we were just given the magnitude of our load, right? So this is something, but it's not exactly what we're looking for. But I can go one step further from this and say that the magnitude of our complex power is equal to the magnitude of our source voltage times the magnitude of our load current. And since we just need the magnitude of the voltage drop across the capacitor, this is actually all the information that we need, right? So rearranging this guy, we'll find that the magnitude of our source voltage is just the magnitude of our complex power divided by the magnitude of IL. So what's the magnitude of our complex power supplied by our source prior to power factor correction? It is indeed. So 16,104.660 volt amperes divided by 21 amps RMS So let's see. The magnitude of what I have stored in my calculator is Z divided by 21. Gives me a voltage of 766.889 volts RMS. And this is the magnitude of the voltage drop across our capacitor. So we now have all of the different constituent parts. So C is going to be 9,863.7 watts times the tangent of theta old, 52.23 degrees, minus the tangent of theta new, which we found to be 18.195 degrees. Divided by omega, which was 120 pi radians per second, times the magnitude of the voltage drop across our capacitor, 766.889 volts RMS squared. And now I can just throw this all in my calculator. $766.889 squared. I got, divide that by 10 to the minus 6. $42.793 microfarads. I might have. Okay. Okay. Alrighty. So that is about the hardest power factor correction problem you could possibly face. Well, actually, it definitely will be, because I'm telling you explicitly it won't be that hard on the exam. And that's the hardest homework problem of this set. So power factor correction is done. You have an in-class assignment that you can work on, and you have a lab that you need to do. So do it up. Thank you, guys. If you haven't already done the evals and all that kind of jazz, please do it.